All right, so welcome all of you again to this second day of the workshop on deep reinforcement learning. Today we have Professor Dimitri Bertsekas from Arizona State University. Uh, so I'll briefly read out his very impressive bio. So Professor Bertsekas did his undergrad studies in engineering at the National Technical University of Greece, Athens in Greece. He did his MS in electrical engineering at the George Washington University and his PhD in system science at MIT. He has held faculty positions with Engineering Economics Systems Department at Stanford, the Electrical Engineering Department at the University of Illinois at Urbana, and for nearly 40 years he was with the Electrical Engineering and Computer Science Department at MIT, where he served as McAfee Professor of Engineering. And in 2019, he was appointed full-time Professor of Computational Decision Making and a full-time faculty member at the School of Computing and Augmented Intelligence at Arizona State University. And his research spans several fields, including optimization, control, large-scale computation, and is closely tied to his teaching and book authoring activities. He has written numerous research papers, 18 books, research monographs, several of which are used as textbooks in and I'm sure across the world. Professor Bertsekas was awarded the Informs 97 Prize for Research Excellence at the interface between OR and computer science. For his book on neurodynamic programming, the 2001 ACC John R. Ragazzini Education Award, 2009 Informs Expository Writing Award, 2014 ACC Richard Bellman Control Heritage Award, and so on. He has a large number of, he has received a large number of accolades and recognitions. His recent books are Introduction to Probability, Convex Optimization Theory, Dynamic Programming and Optimal Control, which is very widely followed in IISc as well, and Convex Optimization Algorithms, Abstract Dynamic Programming, Reinforcement Learning and Optimal Control, Rollout, Policy Iteration and Distributed RL. So these last two books have been published within the last couple of years. And his talk today is going to be again based on a book that he is writing, and that will appear, I think, in early next year. So with that, let me just request Professor Bertsekas to begin his lecture. Professor Bertsekas, over to you.
Okay, thank you for your introduction, Shalab. And you see the title of my talk. It's also the title of my book that's coming out next year. There's a fairly complete draft of the book at my website, and there's some video lectures, a copy of the slides. And this book is based, for the most part, on visualization and conceptualization. However, it uses a lot analysis from my earlier books, in particular the 2020 book on policy iteration, distributed reinforcement learning, and also the abstract dynamic programming book from 2008. I have a problem with advancing the slides, which plays backgammon, and it's 25 years old. At the time it was introduced, was a great success. It created a lot of enthusiasm. It was sort of the AlphaZero of the day. And it turns out that both AlphaZero and TD-Gammon have a very similar structure, and they also involve two algorithms. And some people don't realize that there are two algorithms involved in these programs. One is the offline training algorithm, whereby the program learns how to evaluate positions and how to select moves at various positions. And then there is the online play algorithm, which is the algorithm that generates moves online in real time against human or computer opponents. And it does that by multi-step lookahead, rollout, cost function approximation, a lot of the things that it learned offline are being used in online play. Now, all of this has strong connections with dynamic programming, policy iteration, IRL type methodology, and approximations. And what we're going to try to do in this lecture is aim to understand the methodology so that it applies more generally, and also bring out the connections with control system methodology, MPC, model predictive control, and also adaptive control. There are relations to other methodologies, for example, discrete optimization, but I'm not going to have time to go into this. So let's look at the online play algorithm first for these programs. AlphaZero, AlphaGo, TD-Gammon, they share with some differences the same structure. And the blue stuff here is what the online play algorithm does, but it uses the offline training at 2 points. This red stuff here, it gets a position evaluator from the offline training and also a base player. The online play algorithm uses the results of offline training, and it plays as follows. At a given position, after playing, let's say, k moves at state xk, it generates a look-ahead tree of moves and counter moves up to a certain depth. Then, from the leaves of this tree, it simulates the base player for some more moves, and then at the leaves of that process, it evaluates the position through the position evaluator. So it approximates the effect of future moves by using the position evaluation at these terminal nodes. Then it backs up the scores. It backs up this position evaluation to the root node of the tree, and it calculates evaluations or scores of all the available moves at the root, and then plays the best move. So that's how the online player plays, but with variations. For example, AlphaZero does not involve this middle portion. AlphaGo has some version of this middle portion. TD-Gammon relies very strongly on this middle portion, the rollout portion. The name rollout was coined by the originator of TD-Gammon, Jerry Tesoro, and I'm using the term here in exactly the same way that he has used it. Okay, so now let's go into offline training in AlphaZero. It is policy iteration with approximations using self-generated data. What it does, it generates a sequence of policies or players, and the current policy is used to train an improved policy, and the process is repeated several times. And this current player is evaluated by playing many games, and then its evaluation function is represented by a neural network, a deep neural network, a value network through training. And I'm not going to go into details of the training. Now, given the policy evaluation of the current player, we improve this player by using some form of multi-step look-ahead. It's called Monte Carlo tree search, and I'm not going to get into the details of that. But this policy improvement provides data to represent the improved player by a policy neural network. So there are two neural networks here, value network, policy network, representing the results of policy evaluation and policy improvement. And this keeps going until at some point it stops and the results are fed to the online player. Now, TD-Gammon uses a similar algorithm for offline training. Again, policy iteration. The policy evaluation method was TD lambda at that time. And it generates a value network, but it does not use Monte Carlo tree search, which I don't think is fundamental. and it does not use a policy network. The policy network, the effects of the policy network, the functionality of the policy network is replicated by using the value network. So that's what we have here. Two different algorithms, offline and online. And the offline algorithm is a form of policy iteration. And now here are some empirical observations that I think are important for this online player. The first is that the online player of AlphaZero plays much better than the offline trained player. This is just a fact. AlphaZero plays online phenomenal chess. The offline trader plays a mediocre level of chess by comparison. So that's an interesting fact, that by passing to the online play algorithm, we can improve tremendously the results of the offline training. Another fact is that TD-Gammon plays much better with this middle portion, which involves policy rollout, than without rollout. Tesoro had two algorithms. One was around 1991, which was what you see here, but without the middle portion, the truncated rollout portion. Then in 1996, he introduced the middle portion and the general concept of rollout within this setting, and obtained a much better player. The player from 1991 was subhuman performance. The player of 1996 was superhuman performance. It has not been improved since that time. It's the best backgammon player that there is. So what we'll try to do is try to explain these empirical observations and provide some insight into the process involved in this online training and offline and online play, and aim for generalizations that would apply to control problems, for example. And we're going to use the methodology of abstract dynamic programming, abstract Bellman's iteration. We're going to use visualization a lot, and we're going to focus on the central role of Newton's method. This is the key new research related to my talk, the role of Newton's method and how it enters the picture. So let me summarize the principal viewpoints of this talk. The first is that online play is just a single step of Newton's method for solving the Bellman equation. This is true in the case of one-step lookahead. In the case of multi-step lookahead, each Newton step is preceded by value iterations, some first-order iterations, and it can be viewed as a special case of what's called in numerical analysis Newton SOR. SOR stands for successive over-relaxation. So it's either Newton's method or Newton SOR, but it's still, there's a Newton step somewhere in there. Now, the role of the offline training algorithm is to provide the starting point for the Newton step. But the online play is the real workhorse. That's where everything is happening. The big gain in performance is happening using online play. Offline training plays a secondary role, according to my viewpoint. And the major reason for this is that online play is an exact Newton step. It's not degraded by neural networks approximations like the offline training is. So it inherits all the power of Newton's method. Another point I want to make is that there may be a lot of differences in how online training is done. It may be done by temporal differences, it may be done by aggregation, it may be done by Q-learning. All of these affect the starting point for the Newton step, but they are pretty much washed out by the Newton step. The Newton step is a big equalizer and generates similar results for methods that, for offline training, that may seem different. There's a certain cultural difference between AI and control, which we will aim to bridge. Reinforcement learning as practiced by the AI community is focused largely on offline training issues, whereas model predictive control and adaptive control as practiced by the control community is focused largely on online play and also on issues of stability that are not addressed almost at all by reinforcement learning as practiced by the AI community. I'm going to get later into adaptive control, where the system is changing over time. And I'm going to suggest an adaptation and a variation of adaptive control, so that instead of using reoptimization based on a currently estimated model, it uses a Newton step. This Newton step is applied to an estimated Bellman equation, which is obtained through the results of system identification. But the point I want to make is that it's still a Newton step and it's very powerful. Finally, all of my discussion applies in great generality. Abstract dynamic programming makes very general assumptions about the state and the control space. They can be arbitrary. It applies to stochastic systems, deterministic systems, hybrid systems, multi-agent, minimax, finite and infinite horizon, discrete optimization, and integer programming. Everything I'm going to discuss applies to all of these contexts because it's couched on the abstraction of and the generality of the abstract dynamic programming formalism. Now, some of these viewpoints may be a little controversial and personal, so I thought I would flash this cartoon here. These two people look at the same number from two different points of view. This guy says it's a 6, and this guy insists it's a 9. And I think this cartoon may have relevance to my talk. Okay, so now let me give you an outline. I'm going to provide a point of reference by introducing discounted and undiscounted infinite horizon problems. Then I'm going to go into abstract dynamic programming concepts and introduce the Bellman operators, Bellman equations, and give you a visualization of what online play does as a Newton step, explain stability issues through visualization, explain rollout and policy iteration, introduce a different visualization for linear quadratic problems where the Bellman operators are replaced by Riccati operators, say a few things about model predictive control and a few things about adaptive control. And I'm not sure I'm going to be able to cover all this, but I'll try. So we take as a point of reference an infinite horizon problem that involves a transition between states governed by this system equation. Xk is the state, Uk is the control, Wk is a random disturbance. The system is stationary, and we're interested in station of X. My symbol for policies is going to be mu, and I'm going to be using universally. This policy must satisfy a certain control constraint, and my computer has frozen for some reason. I don't understand why. Okay, somehow it got back again. I'm sorry about that. Okay, the cost per stage is given by this function g, and it's discounted. This is the cost of the k stage, but alpha, the discount factor, could also be equal to 1. The cost of a policy is the limit of the n stage costs, and it's denoted by j mu. This is the cost function of policy mu, and it's a function of the initial state. And the optimal cost function is obtained by minimizing over all mu. Special cases are discounted problems, which are nice for the case where G is bounded and alpha is strictly less than 1. We have also stochastic shortest path problems as a special case, where there's a termination state. And I'm going to also be making reference to the control MPC type of problems, which are deterministic with a positive cost and a termination state. So these are problems of regulation to the origin, classical problems of regulation to the origin. And I'm going to go quickly through the exact dynamic programming theory for this problem. J star, the optimal cost function, satisfies Bellman's equation, which is what you see here. Minimum over first stage cost plus the optimal cost to go discounted with alpha. This is a functional equation, holds for every state. There's one equation for each state. And it may not be the unique solution of Bellman's equation. That's why I have these question marks here. Depending on the assumptions, it may or may not be unique. The optimality condition, if mu star attains the minimum in the Bellman equation for every x, then this policy is optimal. Again, there are maybe some assumptions required for that. And we have two basic algorithms, value iteration, policy iteration. Value iteration generates a sequence of cost functions that are cost functions of finite horizon problems, starting from some initial condition. And it uses this iteration here. And policy iteration uses a sequence of policies, mu k, and their cost functions. And the initial policy is arbitrary, perhaps subject to some assumptions. And the typical iteration starts with a policy and generates a new policy with a policy evaluation step and a policy improvement step. So now let me go into a major reinforcement learning method, approximate dynamic programming method. Online approximation in value space. What we do here is we replace J star, which is difficult to compute, with an approximation J tilde in Bellman's equation. And whenever we get at the state X, we do this minimization, minimize the cost of the first step plus the cost of the future as evaluated by J tilde. And this minimization gives us a control that we apply at time X. I refer this to one-step look-ahead minimization, one-step look-ahead. Now, there's a multi-step version where at state xk, once we get there, we solve an L-step problem, a finite horizon problem with a horizon L, where we have the costs of the first L stages, and then the cost of the future stages is approximated by using this J tilde function appropriately discounted. And now solution of this finite horizon problem gives us a control for time k and policies for times k plus 1 to k plus L minus 1. So L minus 1 policies and an initial control. And at xk, we apply the first control and we throw away all this other stuff. So both one-step look-ahead and multi-step look-ahead define a look-ahead policy, which I'm going to be denoting by mu tilde. Mu tilde of xk is the control that's being applied at state xk by multi-step or one-step look-ahead. And I'm going to be using these symbols very much and consistently in this talk. J tilde for cost approximation, mu tilde for look-ahead policy. And the key fact here is that the cost of the look-ahead policy, this J mu tilde, is the result of a Newton step to solve Bellman's equation, starting from the point J tilde. This is true for one-step look-ahead. For multi-step look-ahead, it's the result of a Newton SOR step, a Newton step preceded by some value iterations. And the important fact here is that the error from this, resulting from this operation, decreases to zero superlinearly. In other words, the look-ahead approximation error is tiny relative to the cost approximation function that you have used as you're close to optimality. So the Newton step has a very fast convergence rate, and I'm not going to go into the details exactly what this convergence rate is, but it's very fast, it's superlinear. Now I'm going to describe these concepts in terms of abstract dynamic programming and abstract Bellman operators and Bellman equations. Okay, this is a difficult slide. It's crowded, but if you persist and understand it, I think you'll gain a lot of insight. There are two types of Bellman operators. Each policy has a Bellman operator T mu, and it's color-coded by blue here in this slide, and it's given by this expression. So T mu maps cost functions J into cost functions T mu's of J, and the components of T mu's of J for every state are given by this expression here. The red operator is the min Bellman operator, which is obtained by minimizing over all the policies of the over mu of the mu Bellman values. And again, it maps cost functions J into cost functions T of J. And these operators define the Bellman equations. And the important fact here is that J mu is a fixed point of T mu, and J star is a fixed point of T. These operators have some other properties. T mu is linear. That's very important. Linear and also monotone. It's upward sloping. And Tj, being the minimum of linear operators, has a concavity property. Now, to visualize these properties, you have to look into a two-dimensional plane. Unfortunately, J is a function of X. If you have n states, J is an n-dimensional vector. And in 2 dimensions, we can only represent scalars. The true graph of T mu and T involves a function on the horizontal and a function on the vertical. However, we represent them here in terms of one-dimensional slices. We look at slices of this graph, one-dimensional slice in the horizontal and one-dimensional slice on the vertical. And fortunately, the insights that you get from these two-dimensional figures are consistent with what happens in the multidimensional case. So let's look at the blue operators that correspond to policies. If you take a generic policy, its graph is linear, and it defines a fixed point equation and has a fixed point, which is this point here. This point is obtained by intersecting the linear graph of T mu with the 45-degree line. And you project down on the horizontal and you obtain J mu, the fixed point of T mu. This happens for every policy. Now, the red operator, the min Bellman operator, is obtained by taking the minimum, pointwise minimum, over all blue operators. And in particular, for any point, let's say J tilde, the value of T sub J tilde is obtained by looking at all the intersection points of this linear policy operators and finding the minimum. And in this way, you also find a policy that attains the minimum. Now, the min Bellman operator, the red operator, has a fixed point, which is the optimal cost. So now, this is mu tilde is the policy that you obtain by one-step look ahead using J tilde. An optimal policy is obtained by using one-step look ahead on J star. So this blue line here represents the optimal policy. And the red operator, the graph of the red operator, is a lower envelope of the graph of the blue operators. And because it has this concavity property, the line that corresponds to this one-step look-ahead policy defines a supporting plane, a subgradient of tj's of x at j tilde. So this one-step look-ahead policy provides a linearization of the min operator at the point where you use for one-step look-ahead. That's where the interpretation as a Newton step will come. So I'm going to leave this slide and use visualization of the value iteration. Value iteration is this algorithm here, starting from some J0. And in terms of the abstract operator diagram, you start at J0, you find J1, which is T sub J0, then you reflect J1 across the 45-degree line over here, then you find J2 by applying T, this is T sub J1, and then you obtain, you reflect along the 45-degree line, you find J3, and so on. And in this way, you generate, through this staircase construction, you generate the sequence, the value iteration sequence. And of course, the convergence may depend on J0, and it also depends on the slope of T, in particular, whether T is a contraction or not. There's a lot of theory about convergence of value iteration, but schematically, value iteration involves the staircase construction. Now, let me get back to the Newton step. We have the online play algorithm with the J tilde producing a mu tilde. So J tilde is the cost approximation. We do one-step look ahead. We obtain a one-step look ahead policy, and we obtain this supporting plane, a subgradient of Tj's of x for a given x at the and the intersection with the 45-degree line gives you the look ahead policy. But this construction, what it's doing is it just linearizes T at J tilde, and you solve the linearized equation to obtain J mu tilde. But that's exactly what Newton's method does. J mu tilde is obtained by a Newton step starting with J tilde. And that's a key point for this talk. Now, figures like that you'll find in books in calculus, but they usually involve differentiable mappings T, differentiable equations. So do we need this differentiability? Well, the answer is no, because the Newton step can work even without differentiability because T is concave, has concavity properties, and it's also monotone. Now, you may need to impose some assumptions here to guarantee that you rule out some exceptional cases, but usually something can be worked out and you can do some analysis, in particular for contractive problems, like discounted problems, everything works out okay, and this is a legitimate Newton step. And one other point that I want to make is that if you change the starting point of the Newton step, then this has an effect on the cost of the one-step look-ahead policy, but this effect is small. Basically, the Newton step smooths out variations in the starting point because of its superlinear convergence property. And there's a lot of empirical evidence about that in the reinforcement learning literature. Now let me go to the Newton step interpretation for multi-step look-ahead. Let's say L-step look-ahead. Well, online play with L-step look-ahead is simply online play with one-step look-ahead after you perform L-1 value iterations. So how can we represent this visually? We start at some J tilde, we perform some value iterations, and then take the Newton step. So the result of this is the result of the Newton step starting from TL-1, L-1 value iterations applied in J tilde. And So the linearization is done after J tilde is enhanced with L-1 value iterations. But again, it's a Newton step at the end. Generally speaking, Newton SOR converges faster than pure Newton, but it's more time consuming. And this is consistent with reinforcement learning. Multi-step look ahead is time consuming, but generally works better than one-step look ahead. There's a lot of evidence about that. Now let me go into stability issues. And I'm going to use primarily the MPC context where stability is important. So think of a deterministic problem with positive costs and a cost-free terminal state like the origin. So a problem of regulation to the origin. Now let's look at this figure here. The question is, how do we define a stable policy? And here we have arbitrary state space and control space. So I'm going to use a cost-based definition of stability. We say that a policy mu is stable if it doesn't blow up its cost for every initial state. If its cost does not become infinite for any initial state, we call it stable. Now, this is a very general definition that does not require you to place any assumptions on the state and control space. It could be continuous or it could be discrete. And stability is characterized by the slope of the blue line being less than 1/2. So these policies are all stable. These policies here that have a slope greater than 45 degrees are not stable. And in a one-dimensional, so we define the region of stability to be the set of all J tilde cost approximations for which the look-ahead policy is stable. And you can see from this figure, this one-dimensional figure, that there is a certain threshold to the right of which we have J tilde that are in the region of stability, and to the left, we have J tilde that lead to unstable policies. And this threshold corresponds to precisely the point where the Bellman operator has a slope of 1/2 or a subgradient of 1/2. Now, if you use multi-step look ahead, then the region of stability shifts because you need to start at a point such that after you perform the value iterations, you end up to the right of this point that corresponds to the 45-degree slope. So the region of stability depends on the length of the look ahead, and the threshold shifts to the left as L increases. So the more look ahead you have, the better stability properties you get. Moreover, value iterations push J tilde towards J star and towards the costs of stable policies. And it makes sense to try to push it in that direction. And that gives rise to the rollout idea, which I'm coming to next. So let's, in terms of Newton's method. Okay, so what is rollout? Rollout is simply a single Newton step, starting from J tilde equal to the cost function of a stable policy. So you have a stable policy, and it has the corresponding operator has a fixed point. J mu has J mu as its fixed point. We use this as our J tilde, and what we are going to obtain by one step look ahead is a policy that has this cost function. We're going to obtain a Newton step starting from here. And J mu can be evaluated by simulation. There are a number of many examples of rollout implementations in the literature. but it is a Newton step starting from a particular type of cost approximation, J mu in particular. And an interesting property here is that if you do a rollout with a stable base policy, you're going to produce a stable look-ahead policy. And how about policy iteration? Well, policy iteration is simply a repeated rollout. Starting from a stable policy, we generate a new stable policy and then a new stable policy and so on. So it's equivalent to Newton's. The typical iteration, you have a policy mu k, you evaluate that policy, consider its Bellman operator, find its fixed point, this is the policy evaluation, and then you do a Newton step, the policy improvement to obtain the Newton, the next policy. So the pure form of policy iteration is exactly Newton's method, and it has been known for a long time, starting with the 60s, and there are many contributions along this line in several different contexts. Kleinman's work was for linear quadratic problems at MIT, and was a student of Mike Athens. And then there were other contributions in the Markov decision problem context and other problem types. So the interpretation of policy iteration as Newton's method is well known. And there is a corresponding interpretation of truncated rollout with a base policy, and it's related to optimistic policy iteration, where you evaluate a policy by using a number of value iterations rather than finding exactly J mu. You start with some J tilde and you compute, you do M value iterations where M can be any positive number on J tilde, and then the result, on the result you do a policy improvement to obtain the new policy mu tilde. All of this can be interpreted graphically, and that's also true for the case where you have L-step look-ahead minimization. And then you have a total look-ahead of L plus M. And what matters is the sum. It's not so much the division between L and M that matters, the sum. In other words, the rollout with a policy is an economical substitute for multi-step look-ahead to a certain extent. And that was really the basic insight behind Tesoro's TD-Gammon. He used the rollout with a policy because it's a substitute for multi-step look-ahead, which is very difficult to do in backgammon, but it's cheaper, much faster. Rollout with a policy is much faster than look-ahead minimization. Okay, I'm rushing a little bit, aiming to finish within my allotted time. Linear quadratic problems can also be visualized, but instead of Bellman operators, one can use Riccati operators. And all our earlier visualizations have analogs based on Riccati operators. In particular, let's consider a one-dimensional problem involving this system here. A and B are the parameters of the system. The cost function is quadratic. Q is the coefficient of the cost, the quadratic cost penalty. R is the coefficient of the control penalty. No discounting. And the optimal cost function is quadratic, with K star, the coefficient, being the solution of the Riccati equation. The Riccati equation involves this Riccati operator F, and that's by definition, that's how it is defined. And it defines a concave curve, and similar, and K star is obtained as the fixed point at the intersection of this red curve with a 45-degree line. And a lot of the visualization I gave earlier applies with Riccati operators instead of Bellman operators. Basically, Riccati operators are Bellman operators restricted on the subspace of. The figure on the left considers the normal case where Q is positive. Here you have two solutions of the Riccati, but only one that's positive, that's relevant. There's an exceptional case where Q is equal to 0, and you have two solutions of the Riccati equation. And one is the optimal, which is 0, but there's another one here. And this is a situation where you don't have observability, for those of you that know what I'm talking about. And a lot of exceptional behavior occurs. And this is only an example. There are other exceptional behaviors within this context that can arise in different ways and require analysis. Okay, now I often get this question. Why not just train a policy network and use it without bothering with online play? After all, online play gives you a policy. I can train a neural network to learn that policy. What's wrong with that? Well, this is actually what is being suggested very often in approximation in policy space, using policy gradient methods, random search, and so on. This approach, I will claim, is flawed in the following way. It lacks the exact Newton step which corrects the errors of offline training. And just to give you an example, let's consider a one-dimensional linear quadratic problem where we parameterize the policies. We consider parameterized linear policies with L being the parameter. Now, this L is optimal. L around minus 0.4 is optimal. However, we're going to consider changing L to see the effect of the errors. And let's consider what happens policy with this L here, but without the Newton step. Then around the optimum, you get small errors. But once you deviate somewhat, then you get big errors, big performance losses. If you use the Newton step, one step look ahead with this suboptimal policy, there's practically no loss of optimality. This is the power of the Newton step that you see here. And this is what you gain by using honest to goodness online neural network approximations. Let me say a few things about model predictive control. The classical form of model predictive control applies to continuous state and control deterministic problems with positive cost, and the origin being a terminal state. MPC now is very important control theory, but it is culturally different than reinforcement learning as it's practiced by the AI community. Still, the MPC architecture is quite similar to the AlphaZero architecture and the TD-Gammon architecture, but it places most emphasis on online play, whereas the AI research community places more emphasis on offline training. There are elements of offline training in MPC, like computing offline terminal cost approximations, computing target cubes, safe regions, to deal with state constraints, with which reinforcement learning does not deal very much at all. However, there have been, in recent years, there have been extensions of MPC, and I'll refer you to the recent books by Rollins, Main Deal, and Borelli, Benporad, and Morari, where there are more complicated versions of MPC that deal with stochastic uncertainties, hybrid systems involving discrete and continuous, a mixture of discrete and continuous control spaces, minimax versions, and so on. There have been also recently proposals of MPC that involve policy rollout in addition to multi-step look ahead, using an offline trained policy. And one of these has been called Learning MPC, and I'd like to refer you to the work of Frusolia and Borelli. There's also a recent paper by Lee, Johansson, and Martinson, and I'm also a co-author on that. Let me go now to adaptive control. Here the system is changing, and we estimate it as it changes. So we collect data from the system, we estimate a new model, and we feed it into an adaptive controller that makes appropriate adaptations. And in the classical indirect adaptive control literature, we simply re-optimize the controller. We have a new model, so we re-optimize the controller from scratch, and then we apply the control that's always optimal for the current model. Now, this is fine, it has its pitfalls, but it works fine in practice, generally speaking. On the other hand, re-optimization is a difficult and time-consuming operation in many cases. So what I'd like to recommend is a faster alternative, indirect adaptive control by using rollout with some policy, preferably a robust policy that's reasonably good over a range of system parameters. So we use rollout in place of optimization because this is simpler, and it can be implemented perhaps with using a lot of computational resources, and capitalizes on the fast convergence property of Newton's method. And let me give you an example. We have, in this example, the system is one-dimensional. It's a quadratic cost. B is the parameter that changes. R also may change. We are going to use one-step look-ahead and rollout with a base policy that's optimal for these nominal values. Now, these are the nominal values, and we have a base policy that's optimal for these values. And but we're going to use that base policy as this B parameter changes. And if you were to use adaptive reoptimization, you would obtain this green curve here. However, there's a performance loss if you don't do any reoptimization, any adaptation. The alternative to reoptimization is adaptive rollout. And there is hardly any difference in the performance between reoptimization and rollout. This is the power of the Newton step. So in this figure, we change B. In this figure, we change R, and there are similar results. So my conclusion is that using a robust controller as base policy, but without the Newton step, without reoptimization or a Newton step, often produces results that are unsatisfactory. However, if you use the Newton step on top of a robust controller, then this flaw is corrected. Okay, so it's time to wrap up my talk, and I'm going to show you in red the main points that of this work. The first point is that there is much to be gained by using online play on top of offline training. If you use just offline training without online play, it may not work well because you don't have the exact Newton step that can deal with changing system parameters and training errors. If you use just online play without offline training, we may miss out on performance because offline training can produce good starting points for the Newton step. The other point I want to make is the role of Newton's method is central here, and this is a new insight which, through the graphical interpretations, can guide both analysis and algorithmic design. Let me reiterate that the Newton step is exact. All the approximation, the RL type of approximation, goes into the starting point of the Newton step. And the Newton step tends to wash out the errors and the method differences that go into training. I think that the cultural divide between the AI community and the control community can be bridged by bringing together offline training and online play. After all, MPC uses an architecture that's pretty similar to AlphaZero's, except that it doesn't use the offline training that AlphaZero does. We can enhance MPC by using rollout with a base policy, and we can approach also indirect adaptive control through rollout, which is a reinforcement learning concept, use a Newton step in place of reoptimization. The last point I want to make is generality. Everything I discussed through the abstraction of through the abstract framework of dynamic programming applies to arbitrary state and control spaces. In particular, beyond the MPC and adaptive control context that I've discussed, it applies to discrete optimization contexts and also other contexts like multi-agent optimization. A lot of this material on discrete optimization, multi-agent, I haven't discussed it here, but there's a lot of it in the 2020 book. Finally, there are exceptional behaviors all over the place when you move beyond the nice discounted MVP case. And all of this requires analysis that in some cases may be quite challenging and quite interesting. So I'd like to close with some words of optimism. I think we have seen tremendous successes from reinforcement learning and model predictive control, and these are solid reasons for optimism. And I think more success can be expected by combining the AI ideas and the MPC adaptive control ideas. A lot is predicated on online look-ahead with minimization or rollout, and this can be a computational bottleneck. On the other hand, we have massive computational power. We will have more computational power in the future, as well as distributed computation, and all of this is a source of hope and will allow more sophisticated online play strategies. So all in all, it's an exciting journey ahead, and I thank you very much.
Thank you very much, Professor Bertsekas, for that absolutely wonderful talk. We